Okay, now we are looking at enzyme inhibition kinetics. And in class, we've talked about inhibition, the different types of inhibition, where we look at the reversible and the irreversible inhibition. And we looked at suicide inhibition, and then we look at reversible inhibition, and we talked about the three forms of reversible inhibition, or the three types. We have the competitive, the non-competitive, and the uncompetitive inhibition. We talked about the competitive inhibition and its various forms. But this lecture is specifically for the kinetics of the inhibition. How do we get the Ki? How do we get the Km? How do we get the Vmax? In the place you have done an inhibition experiment and your data have been generated. So let's dive into the study. Now, we are going to start with competitive inhibition. And in competitive inhibition, we look at a situation where the inhibitor is competing with the substrate for the active site of the enzyme. Okay, the active site of the enzyme. So we are presented with two equations, the one you see horizontal and the one you see vertical, where the enzyme binds to the substrate to give you an ES, and then the ES is being broken down to enzyme and product. Okay, and also we said in the E2, in the equation 2, the enzyme binds to inhibitor and does not give room for the substrate to bind, so no product is formed. So the two equations we are looking at, basically the equation 1 and 2, is E plus S going into ES, and then ES is broken down to EP, E and P. Then you have the second one, the enzyme and the inhibitor, E plus I, giving you ES, and the reaction can no longer proceed. Now, considering the first equation, which is similar, we've done that when we are looking at steady state kinetics. Now, when we look at our rate constant K1 and K2, you know, you saw that K1 is equal to ES over E multiplied by S, and K2 is equal to the inverse because it's a forward and a backward reaction. We are looking at equilibrium. Now, let's look at the formation of ES. And we say that the formation of ES, or the rate of formation of ES, is K1 multiplied by E and S. The breakdown of ES is the normal way, which is K2 multiplied by ES plus K cat multiplied by ES. Okay, now when we consider the steady state assumptions, where we say that the rate of formation of ES is equal to the rate of breakdown of ES, and breakdown is in two ways. ES is broken down to E and S, and also ES is broken down to E and P. I've explained that. Now, when we weight these two rate constants, or rates of formation and breakdown, we have that K1 multiplied by enzyme concentration multiplied by substrate concentration will give you K2 multiplied by ES complex and the plus K cat multiplied by ES complex. So you go down and you now come to a place you find out that ES is equal to K1 over K2 plus K cat, all multiplying enzyme concentration multiplied by the substrate concentration. Now that is our equation 3. But we introduce a new constant, the Michaelis-Menten constant, or the Michaelis constant. Now we say that this Michaelis constant is the sum of the rate constants for breakdown or backward reaction all over the rate constant of formation or forward reaction. So Km is equal to K2 plus K cat all over K1, of which 1 over Km is the inverse. So we replace that 1 over k1 over k2 plus k cat, we are going to replace it with the inverse of km in our question 3. And when we do so, we have that Es is equal to E multiplied by S all over km. Now, always remember that the rate of reaction will always be k cat multiplied by Es, because Es is broken down to give you the product. So when we substitute what Es is, we have our equation 6. Now, let's look at what happens in the other reaction 2, in our equation 2. So we do the same. The for reaction, or the rate of formation, the rate constant for formation of EI is K4, and the rate constant for the breakdown is K5. Okay. Now, if you consider the same steady state assumption, the rate of formation of ES will be equal to the rate of consumption of ES. So K4 multiplied by E multiplied by I is equals to K5 multiplied by EI. So we can make EI the subject of the formula, and we have that. Now we introduce another constant, which is the inhibitor's constant. We explain these constants when the time comes. Now the inhibitor constant is the rate constant of breaking down or backward reaction of the inhibitor all over the rate constant or rate of formation of the EI complex. What the inhibitor is, we are looking at the formation and breakdown of EI. Okay, so 1 over Ki will give you K4 over K5. Now, when we substitute that, we have that EI will be equal to the E multiply I all over Ki. That's equation 8. So now we have different enzyme species. So let's look at the conservation. That in this particular reaction, we are looking at, we have free enzymes, we have enzyme bind to the inhibitor, we have enzyme bind to the substrate. Okay, now when we substitute this, because we look at conservation of energy, we assume that there is no way an enzyme, the total enzyme in a system, will diminish, okay, but rather it is converted from one enzyme form to the other. So the total enzyme will always remain free enzymes plus enzyme bind to the inhibitor plus enzyme bind to the substrate. And if that holds, we remember that our Es is equals to enzyme concentration multiplied by substrate concentration over Km, and the EI is enzyme concentration multiplied by inhibitor concentration all over Ki. So we have to replace that in the total enzyme. And when we do that and factorize and make E the subject of formula, we have what is left in equation 10. Okay. Now, from our equation 6, we see that K cat multiplied by E is the free enzyme over S, multiplied by S divided by Km. Then, because I wanted to readjust this, okay, you see how I've written it so that we can replace that E, and we are not going to find it difficult from where we placed it. So the E, which we have gotten, the free enzyme, as E total all over 1 plus 1 over I over Ki plus S over Ks. So when we use it to replace X in the above, you will have your V, and you follow the reaction until you get to the last point. Okay, you get to the last point. Now VO is equals to V max X all over Km into 1 plus I over Ki plus S. The I there is the concentration of the inhibitor. Okay, now when we have gotten that as the equation, the Michaelis-Menten equation for a competitive inhibition. Now, if we make a plot of 1 over V against 1 over X, for the the uninhibited reaction, okay, that is the line you have there that is in blue, and then the inhibited reaction, that is the line that you have in red. We found out that this in this one of the intercept on the vertical axis is not changed, okay, and this shows you the mechanism of inhibition, while you see that the Km is changed or affected by a common factor. So in competitive inhibition, the slope change is not the same, the Km is not the same, but the Vmax is the same. So what is it telling us? What it's telling us in the summary is that competitive inhibitor binds to free enzyme and competes with substrates for the active site, okay, and that is why the rate of binding or the affinity of binding is affected in the Km. Now we say that this part of inhibition raises Km without affecting Vmax, and the only way we can solve this problem is to increase the concentration of substrate. So always know this. With this, you can actually determine your Ki, because when you know the value of your Km and your Vmax, the other ones that are there will be for substitution. And I want you to know that the concentration of the inhibitor is always kept constant throughout the experiment. You can't be varying two of them. Now, let's look at uncompetitive inhibition. In uncompetitive inhibition, the inhibitor does not bind to the free enzyme form. Rather, it binds to the ES form, and when it binds, the reaction will not proceed. So what we are looking at here is that when substrate binds to enzyme, the conformation of the enzyme will change to enable the binding of the inhibitor. So inhibitor does not, an uncompetitive inhibition, it does not bind to the free enzyme form. It only binds to the bound enzyme form. So here we have two equations we are considering again. Equation 1 being the normal enzyme plus substrate to give you ES, which is broken down to enzyme and product. And then we have the second one where the ES, the enzyme complex form, binds to the inhibitor. And once this ternary complex, which is ES, is formed, the reaction will not proceed until such inhibition is removed. So let's look at the kinetics and what we can get from it. Now the first one is what you have already known, that ES to E plus S, goes to K cat, and that we have that ES at the base will be equal to K1 all over K2 plus K cat. We have done this, okay? Just go through it. You can pause the video and take time to go through it. Now, well, let's look at okay, let's look at equation 4. So we say that ES is equals to E multiplied by S over Km. So introducing the initial rate of the initial velocity, which is VO, equals K cat multiplied by ES. So if you replace ES, you're going to have that VO is equals to K cat multiplied by E plus S all over Km. Now let's go back to the other equation. So we look for the rate constants K4 and K5. So the rate of formation of ES is equals to K4 plus the ES multiplying I, while the breakdown is ES multiply the breakdown of ESI will be equal to K5 multiplied by ESI. You can see that in the reaction above. So if we normally consider our steady state assumption, rate of formation of ESI will be equal to rate of breakdown of ESI. So we have K4 multiplied by ES multiplied by I will be equal to K5 multiplied by ESI. So making ESI the subject of the formula, we see that K4 over ESI will be equal to K4 over K5, multiplying ES and then multiplying I. But we need to introduce another constant, which is the inhibitor constant. So by definition, we say that the inhibitor constant is the rate constant for the breakdown or backward reaction of the inhibitor. Okay, and this backward reaction for the inhibitor, we are just talking about the formation of ESI. So when you look at 1 over Ki, you will find out that you're having K4 divided by K5. Okay, so when we do that and plug it into our equation 7, we have that ESI is equal to ES multiplied by I over Ki. Okay, so we are going to substitute ES, which is in equation 4. We are going to plug it into equation 8. And when you do that, you will begin to find out that ESI will be equal to E multiplied by S multiplied by I all over Km multiplied by Ki. So you look at law of conservation of enzyme again. Okay, and we substitute for ES and we substitute for ESI, so that we have so that we have an equation that will give us free enzyme. So when we replace that, we have that E total is equal to ET plus E over ES over Km plus ESI over Km multiplied by Ki. Now, when you factorize, you will have that ET is equals to E multiplied by those factors, and then we make E the subject of the formula to give us it. So the free enzyme is now known by that equation 11. Okay, now, well, from equation 6 we already have that. So if we substitute E in that equation, is going to give us our equation. Just pause the video and go through how it's being calculated, and then at the end of the day we have that VO is equals to Vmax multiplied by S all over K multiplied by plus S multiplied by that factor. Okay, now let's look at the summary. Let's look at the summary. Now, when you make a plot of 1 over VO against 1 over Vx, you will begin to see the normal blue line representing the uncatalyzed reaction, and the one in red is for the catalyzed reaction. Now, one thing you know is that these graphs will form two parallel lines, showing that for uncompetitive inhibition, it affects the VI, it affects the Km and it affects the Vmax. It affects the Km and it affects the Vmax. Okay, and it affects these two by a common factor, which is 1 plus I over Ki. Okay, now I want us to really look at this. Let's just look at the summary. We say that non-competitive inhibition binds to the ES form, and when it binds to the ES form, it prevents substrate from binding, and also it prevents the complex from breaking down to go into products. So we say that it lowers both the Km and the Vmax, and the ratio, but the ratio of Km over Vmax, which is the slope, remains the same. And we say that this also occur in multi-substrate enzymes. Okay. Okay, so I would also want you to take time and go through this. Now, finally, we look at the non-competitive. Now, in non-competitive, the inhibitor can bind to any of the enzyme forms. So the inhibitor does not bind to the active site. It binds to the allosteric site. Okay. Now this inhibitor does not prevent substrate from binding, and it does not bother whether it has an ES form. So in this particular type of inhibition, we are looking at 4 equations. When the enzyme binds to substrate, when the enzyme binds to EI complex, when the enzyme binds to when the EI binds to S, and when ES binds to I. In fact, in this inhibition, the binding of S does not in any way affect the binding of I. But the truth is that once the ESI is formed, the reaction cannot proceed. Whether inhibitor binds first or whether substrate binds first is not the issue. The issue is that once ESI complex is formed, there is no product formed. So let's continue. If you have understood this, take your time to understand it. Okay, I said things to know about non-competitive inhibition. The inhibitor binds to another site on the enzyme which is not the enzyme active site. The binding of the inhibitor does not affect the binding of the substrate, which I have said. Now, because of the above 2 points, the inhibitor can bind to free enzyme and also bind to enzyme substrate complex, while substrate can bind to free enzyme and bind to enzyme inhibitor complex with the same affinity. Now, but when the enzyme substrate inhibitor complex is formed, the catalytic activity or property of enzyme is affected. Now, because of the enzyme and the inhibitor binding freely to because of this, the enzyme and the inhibitor binding freely to enzyme, from that previous slide we just left, we find out that K1 is and K6 will be equal. You will also notice that K2 and K7 will be equal, K4 and K8 will be equal, K5 and K9 will be equal. So always try to write down this and make reference to know the reason why they are equal. Okay. Okay, so let's start. This part of the equation is very new to, it's not new to you again. So you go down and look at it, okay, and then until you get to VO, which is equal to K cat multiplied by E and multiplied by S over Km. Good. So when you've gotten to this place, we wait and go back to our enzyme forms. Now, okay. Now, let's look at EI. the EI formation and the EI breakdown, we make EI to be equal to K4 over K5, all multiplying E and I in equation 7. Okay, now you introduce your inhibitors constant, and you have that EI will be equal to E multiplied by I all over Ki. We saw that in our when we are looking at the uncompetitive inhibition. Now, let's consider ESI, and we know that ESI is formed from two different sources, either the substrate binding to EI complex or the inhibitor binding to the ES complex. So now we are going to have two ways of forming ESI, either by the rate being K8 into EI multiplied by S, or K6 multiplied by ES multiplied by EI. Okay, for the breakdown, it is either ES is broken down in the form K9 multiply ES or K7 multiplying ESI. So when we consider the steady state assumption, where we say rate of formation of ESI will be equal to the rate of breakdown, since we are dealing with ESI, we are going to be working looking at it side by side. We are going to be looking at it side by side. Okay, so it is either we consider the E8 multiplied by EI multiplied by S being equal to K9 multiplied by ESI, or we'll be looking at K6 multiplied by ES multiplied by I is equal to K7 multiplied by ESI. Okay, now this constant K8 over Ki is an inhibitor constant which we introduce, and we call it Ki prime. Ki prime. Now for the other side, we call it Ki prime prime, just for us to differentiate it. So if we consider the one with Ki prime, we say but EI, which is in the equation, okay, is equal to um, um, E multiply I all over Ki. So when we introduce it to our ESI, you find out that our ESI will now be E multiplied by S multiplied by I all over Ki multiplied by K prime prime. On the other hand, if we consider the other part of the equation of the ES formation and breakdown, we see that ESI also will be equal to E multiplied by S multiplied by I, all divided by K prime prime I multiplied by Km. Now, the question is, which of the two ESIs should one use? Okay, and over the years I've done this, I always prefer to use the one in which Km is present. Okay, in which Km is present. There are some other things we are going to see while going through this. Now let's look at the law of conservation of enzyme. Okay, now we have 4 enzyme forms. So we have that total enzyme will now be equal to free enzyme plus plus EI plus ES, then plus ESI. And we know the equations for ES, EI, and ESI. So we are going to substitute them in this total enzyme. Okay. Now, when you do that, you find out that making E the subject of the formula, you're going to have E total multiplied by 1 plus I over Ki plus S over Km plus S multiplied by I over Km multiplied by K prime prime. Remember, I told you I prefer using the one in which Km is present. You can use the other one and fit it in. Let's see whether we will have the same answer. Now, knowing that KVO is equal to K cat multiply E multiply S all over Km, we are going to replace our E. Okay, I use different colors to show you where the E is replaced, and then we will now cancel the ones that should be cancelled and the ones that should not be cancelled. Okay, so when you open the brackets in the denominator, you will have Km multiplying all through, and when you do that, you will have that VO is what you have below. Now, we now say that that we know that Vmax is equal to K cat multiplied by that, so you input that in that equation and you arrive to the equation in green, which is VO all over V, and VO is equal to Vmax multiplied by S all over Km multiplied by Ki multiplied by Km multiplied by 1 plus I over Ki is equal to x plus 1 over I over Kn. Now, at this point, I want you to know that when you look at that equation critically from the first point, we find out that K1 is always equal because of the free binding nature. S is binding the same way I binds to free enzyme is the same way I will bind to bound enzyme. So it is not affected, and that makes K1 to be equal to K prime prime. So if that is the case, we then have the final equation as Vmax multiplied by S all over Km plus S, all multiplied by 1 plus I plus I over Ki. Okay, this is exactly what I was trying to explain in that. I said because the binding of the inhibitor to the enzyme is not affected by substrate, and since the binding of the substrate is different from that different from the inhibitor, so Ki will be equal to K prime prime I. Now, when we have this equation as the final equation, let us simply summarize. When we look at this, because the binding of the inhibitor does not affect the binding of the substrate, Kn is not affected. So for non-competitive inhibition can bind to free enzyme and it can bind to enzyme substrate complex. We said it lowers the Vmax, but the Kn remains the same. Non-competitive inhibition does not bind to X binding site, therefore does not affect Kn. What does it do? It offers the conformation of the enzyme to affect catalysis, but not substrate binding. Okay? When it binds, what is affected is catalysis, but it doesn't affect whether substrate binds or not. So I hope that is clear. In the next class, we will take an example. In the next video, we take an example of a plot and then use that plot to determine the mechanism of action or the mechanism of the reaction. Sorry. Okay, we are going to wrap it up here. Thank you very much.